Hello everyone. In this presentation, we'll be covering our poster for our project, In Situ Conformal 3D Printing for Targeted Repairs. 3D printing is typically used by hobbyists or for quickly prototyping parts, but the technology has also recently garnered interest in more complex projects like rocket engines, bone repair, and even manufacturing in space. For this reason, reparative printing is gaining attention as a potential solution for maintaining the health of these projects over time, in addition to more general repair applications. So our primary research question is, how effective is 3D printed structures with conformal 3D printing? Where conformal 3D printing is a method which allows for printing on non-planar surfaces.
To begin to answer this research question, we used an Ender 3 Pro 3D printer to print simulated damaged test samples. We chose to look at samples with a triangular and hemispherical cutout. After printing the damaged pieces, we let the sample cool and ran a repair print using the same printer. We chose to vary different properties of this repair print in our project.
For our research, percentage infill, tension versus compression, and infill pattern were chosen as our properties to test. The control for all our experiments are 6 hole-printed 100% infill samples, which simulate undamaged 3D printed parts. 6 T1 and 12 T4 damaged geometries were also tested to find the lower bound of an unrepaired part. The number of samples in all our tests abide by the ASTM standard. For infill testing, 6 parts at each of 5 different infills with the T1 damaged geometry were tested. For infill pattern testing, both the hexagonal and concentric infill pattern had 12 T1 parts printed at 40, 60, and 80% infill. For tension versus compression testing, each of the 2 damaged geometries had 6 parts tested with the repairs in compression and 6 parts in tension. Without access to a testing facility, a custom 3-point bend test apparatus was created to conduct our experiments.
Our method for testing the strength of these various repairs is by performing a 3-point bend test on each of the samples. Without access to campus labs and equipment during the pandemic, we had to design our own testing apparatus. So using data from a force sensor mounted onto a hydraulic jack and a strain gauge glued to the bottom of the sample, we can derive a full structural analysis of the beam. We also have steel D-shafts at the supports and loading point to try to make sure all the forces on the sample are each applied only at a single point along the length, which is important for accurately analyzing the bend test data. When we conduct a test, the sample is placed on the supports so that the damaged or repaired area is directly under the loading point. By pumping the lever, which you can see in Figure 6, we gradually increase the amount of force on the sample until there is total structural failure. During this whole process, the force sensor and strain gauge are continually recording data, which pass through an Arduino and then organized for further analysis.
Now we will discuss the results from the data we have gathered. The most prominent data is on the graph on the right that shows the difference in load that the different specimens were able to carry. This shows how the repaired samples are able to hold more than the damaged samples. We also took strain data when possible, and were able to see that the Young's modulus is slightly higher after repair than it was before. To rank how effective the different samples are compared to the undamaged samples, we generate the percent effectiveness based on the max load held. The closer to 100% or higher, the better. As you can see, when the repair is in compression, it actually outperforms the undamaged samples. Finally, we have begun looking into the differences caused by altering infill pattern and percent infill. This data is incomplete, and we are continuing to take more data to see any patterns. From our results, we are able to see that repair causes a statistically significant improvement in maximum load held compared to the damaged samples. We will need more data to figure out what repairs improve damage the most, and how to best optimize it. We also found preliminarily that 80% infill is optimal instead of 100%, as other literature has shown in general 3D printing. An unexpected result that we found is that when repairs are in compression, they actually hold more load than the undamaged samples. More research needs to go into finding why this is the case.
For our future work, we have many goals planned. These include using our T1 designs to test different infill patterns to find the best pattern, test different damage types for improved repair methods, testing using different materials, finding optimized parameters using multivariate data analysis, performing analysis to support why damaged parts perform better compared to its undamaged counterparts for compression, and finding the parameters that are most vital in obtaining information about damaged regions. While this project limits testing to primarily plastics, it is equally possible to perform reparative printing on other materials such as metal or biological tissues.